So we last left off with patterns on the periodic table. And actually, let's go back and take a brief look at these. So periodic table is mostly made up of metals. So all of this beige, these are all metals. And then there's a small sliver, just a handful of metalloids, and then everything else is nonmetals. So the metals will all always be positive charges. The metalloids you don't have to worry about, except for maybe arsenic, but that's polyatomic ions, which that quiz is today, polyatomic ion quiz. But again, like the other quizzes, retakeable. So if you're just absolutely not ready today at all, that's fine. Just take it future weeks. The nonmetals are always going to be negative charges. As far as properties go, you know what metals are, right? Your intuition about metals is correct. They are usually shiny. They're sort of malleable. They've got these other properties, like they can be stretched into wires, pounded into flat sheets. That's malleability. They tend to lose electrons. And remember, we can't lose protons or gain protons, because that changes the identity of the atom. But we can lose or gain electrons. So if you lose electrons, you then have more positive charges than negative charges. That's why they are form positive charges. The nonmetals are in between, or sorry, nonmetals. Oh, okay, goes nonmetals first. The nonmetals are right side of the periodic table. They're either like brittle solids, or they're powdery, or they're gases. They don't really conduct electricity, unlike metals. And when they undergo chemical changes, they gain electrons. So you gain electrons, you have more negative charge than you have positive charge. So you have an overall negative charge. That's why they form negative charges. And then the metalloids lie along that little zigzag. There aren't very many of them, but they have properties in between metals and nonmetals. So we went through these. Another way that we group the periodic table is in terms of main group elements and transition elements. So the two taller sections of the periodic table are the main group elements. Then everything in this lower section are transition elements, or transition metals, because they're all metals. For the main group elements, properties are fairly predictable and are going to be mostly based on what column they're in, what group they're in. So then this is taking that categorization of like, we can break the main group metals into further smaller categories. Those are on the left side of the periodic table, the alkali metals and the alkaline earth metals, which are just names for elements that have, well, elements in the same group, which have similar properties. And then on the right side, there are the halogens and the noble gases. So the group 1 metals, or the alkali metals, they form the +1 charges, right? They all form +1 charges. They are very reactive. We'll talk more about why when we get to electrons. But things like sodium, or lithium, sodium, potassium, rubidium, and cesium, and these get even more reactive as you go down the periodic table. Next category are the alkaline earth metals, which are fairly reactive, but less reactive than the alkali metals. Beryllium, magnesium, cesium, strontium, barium, again, getting more reactive as you move down the periodic table. Then the halogens are very reactive nonmetals. And actually, I'll point out this fact that the alkali metals, everything has to do with electrons. So these alkali metals are very close to having the same number of electrons as the noble gases. Even though they're on opposite sides of the periodic table, for every atomic number that we go up, we're just adding 1 electron. So you see that sodium has 10 protons, sodium has 11, neon has 10. So sodium here has 1 more, neutral sodium has 1 more electron than neon. And if it loses 1 electron, if it can give that away somehow, it'll have the same electron configuration as neon. And the reason it wants to do that is because the noble gases are chemically inert, or very, very stable. They don't react with anything. This is why it's better to use helium rather than hydrogen in balloons, because if you use hydrogen, hydrogen burns, can explode. Helium doesn't. Yeah, hydrogen balloons near birthday candles, not a good combination. Very bad combination. And so the halogens also, I guess we can use these periodic tables, are right next to the noble gases. That's why they are also very reactive. The alkali earth metals, that's group 2, starting with beryllium, those are less reactive than the alkali metals because they're sort of 2 steps away from being noble gases. So less reactive, but still fairly reactive. Noble gases. So which group or family of elements does each element belong to? Well, for lithium. Yeah, lithium's an alkali metal. And that's because it's in group 1. So that whole first column of the periodic table, alkali metals. Let me make sure I spelled that right. Yes. What about B, boron? Does it belong to a particular family? Or what is its group? It is a metalloid. I guess group 3A. So I didn't address this probably. The periodic table, there's 2 ways that you do these numberings. They're the group numbers, and so if it's 1A, 2A, 3A, that's just talking about the main group elements. So the two towers there on the periodic table. The other way to number them is just 1, 2, and then this would be 3, 4, 5. So the number with A skips all the transition metals and gives us groups 1 through 8A. So what group is boron in? 3A. I know what I was asking for there wasn't super clear. What about iodine? It's a halogen, yeah. And argon? Noble gas. Which of these would you expect to be the most reactive? Huh? Yeah, probably lithium. I don't know, actually. Yeah, actually, definitely lithium. I don't know how you would know that it's more reactive than iodine, because both are very reactive gases. Or, well, iodine's a very reactive gas, or solid, actually, at room temperature. Lithium, though, I think would be more reactive. All right, so I've been hinting at this and talking about this a little bit, but ions result from gaining or losing electrons. In chemical reactions, atoms often lose or gain electrons to form charged particles, which we call ions. Positive ions are called cations, and negative ions are called anions. The charge of an ion is shown in the upper right corner of the symbol, so we would write something like Na plus would be an ion, versus Na, which is just the element. And then, I'm not going to be super, super picky about this, but usually if there's a If it's more than just a 1 plus or a 1 minus charge, you write the number first and then the charge. So it'd be S sulfur 2 minus instead of minus 2. A lot of the reactions are actually based on these transfers of electrons between things. So lithium, for example, it's an alkali metal. It's in group 1A. It wants to form a 1 plus charge, so it loses 1 electron to do that. All right, so we have elemental lithium here, no charge. Losing 1 electron, we then get the ion, the cation, lithium 1 plus. You can calculate the charge on an ion depending on how many electrons are gained or lost. So your ion charge is going to be the number of protons minus the number of electrons. So for this lithium plus, with 3 protons and 2 electrons, we get 3 minus 2 equals 1 plus. It says lithium plus sounds like a subscription service. It's like Disney Plus, but for reactive metals. So yeah, ion charge, just take the number of protons, subtract the number of electrons, and that'll give you what its charge is. So if we're gaining electrons, you could write this out as elemental fluorine, so no charge there, adding 1 electron to it, and getting fluorine 1 minus. And so if we were to calculate that out, again, it's still the number of protons minus the number of electrons. So fluorine has 9 protons, and elemental fluorine by itself, no charge, would have how many electrons? 9 electrons also. So anything that doesn't have a charge has the same number of electrons as it does protons. So if we give fluorine 1 more electron, now it's got 10 electrons. That's 10, or 9 minus 10 gives us 1 minus. So it's a negative 1. So if we have a nickel ion, and these are very similar to the type of questions that I would ask on an exam for this sort of thing. If we have a nickel ion with 26 electrons, what charge is that going to have? Yeah, because how many protons does nickel have? 28. Just got to find it on the periodic table. It is Ni. So 28 protons minus 26 electrons is going to be 2 plus. So we'd write that as Ni 2 plus. And then a bromine ion with 36 electrons. How many protons does bromine have? What was it? 35. Yeah, bromine is Br. So 35 protons minus 36 electrons means that we have a 1 minus charge. So it would be Br minus, again, make sure, I don't know if I mentioned it in this class actually. It might have been a different one. Make sure that you're writing the symbols for elements with a capital first letter, and then if there's a second letter, it needs to be lowercase. How about phosphorus with 18 electrons? You can leave if it's 1, you can leave the 1 off, because we wouldn't write a negative there if there wasn't at least a 1 minus charge. That's fine too. Yeah, you could write this. That's also fine. Yeah. Be P3 minus, because phosphorus has 15 protons minus 18 electrons equals a 3 minus charge. So it'll be P3 minus. And then that 3 minus always needs to be an exponent, or in the same spot that an exponent would be, superscript. Yeah.
Technically, we just
Bingo. Yeah. Yeah, as long as you put the protons first and then subtract the number of electrons, it'll tell you if it's a positive or a negative charge. So now you're going to find the number of protons and electrons in the S sulfur 2 minus. So how would we go about doing this? Yeah. So sulfur from the periodic table, we can see it has 16 protons. And then if we've got an S2 minus charge, that means we have 2 more electrons than we have protons. So there must be 18 electrons. You could write it out a little bit more formally if you prefer, because it's the number of protons minus the number of electrons. And we know that that has to equal 2 minus. And then we also know that we have 16 protons minus the number of electrons equals 2 minus. So if we subtract 16 from both sides, we should do be negative 16 minus 16. Then this is going to be negative number of electrons equals negative 18. Then we can divide both sides by a negative. So if you like the math and you like plugging things into formulas and arranging them, you can do it that way. But it's just a little bit of deductive reasoning here to figure out how many electrons there are based on the number of protons. Or I could tell you that there's a certain number of electrons and tell you the charge. And then you could figure out what the element is from that. Oh, okay, this was on the slides. So the number associated, I told you guys about this, but the number associated with the letter A above each main group column, 1 through 8, gives the number of valence electrons for the elements in that column. So that's the number of electrons in its outermost shell. Those are the ones that are actually interacting with other atoms. Everything on the inside is shielded from those outside ones. Kind of like a Russian nesting doll, right, where there's like the smaller dolls inside and the larger dolls on the outside. That outermost doll, those are the electrons, the valence electrons. So looking at the periodic table, you can go 1A, 2A, that's 1 valence electron, 2 valence electrons. For the element form, that's on the periodic table. 3A, which starts at the top with boron, those are 3 valence electrons, 4, 5, 6, 7, 8. So you never need to guess at the number of valence electrons for any element. It's on the periodic table, like so many other trends. And then our main group elements tend to form ions that have the same number of valence electrons as the nearest noble gas. So if we look at something like, we'll do it like this. So if we look at fluorine, fluorine has, how many protons does fluorine have? 9. Right, it's 9 protons. And it has how many electrons? 9. Yep, for elemental, it's going to be 9. So 9 protons minus 9 electrons, that's going to be 0. It wants to have, so this is where it says, tends to form ions that have the same number of valence electrons as the nearest noble gas. So what is the nearest noble gas to fluorine? Neon. And neon has how many electrons? So we said 8 electrons. 10. So fluorine has 9 protons, but it wants to have as many electrons or valence electrons as neon, and so that's why it forms a 1 minus. And that applies to chlorine also, because chlorine's going to want to have 1 more electron than it does right now to get to the nearest noble gas. Bromine does the same thing. And even on, well, even for oxygen, sulfur, and selenium, they are 2 electrons away from the nearest noble gas. So they will form ions that have 2 more electrons than they do protons. That's why they have 2 minus charges. And it applies even to the other side of the periodic table. They just go backwards 1 step. So sodium, like the example I used before, has 11 valence electrons. It will lose one of those to have the same number of electrons as its nearest noble gas, which is neon. And then magnesium will lose 2. So that's why the first column is 1 plus, the second column is 2 plus. And then 6A, which is starts with oxygen, those form 2 minus. Fluorine down forms 1 minus. Because they're all trying to be like the nearest noble gas. And so that's what we see here as well. This really applies just to the main group elements. I did, of course, give you a few others. There's scandium, which forms a 3 plus. There's also, I always forget these two, zinc and cadmium, which form 2 plus, and then silver is a 1 plus. So those are most of the ones that I had you memorize. You can see that, right, these are 2 electrons away from the nearest noble gas. These guys are all 1. 1 and 2 respectively. So based on their position on the periodic table, what ions do potassium and selenium tend to form? Let's do potassium first. What was that? Oh, potassium is K. Yeah. So it has 19 protons. How many electrons does it want to have? 18. So 19 minus 18 will give you 1 plus. What about selenium? As we start with how many protons it has. Yes, 34. And it wants to have 36 because krypton is the closest nearest gas. So 34 minus 36 is going to be 2 minus. So you'll have a periodic table on every exam. And there's a lot of stuff that you can just sort of, if you memorize where it is on the periodic table, then you'll have this concrete guide every time on the exam. And I do think it's worth it to have stuff that you kind of memorize short term that you just write on the periodic table at the beginning of the exam before you start doing any questions. Just write those things on the periodic table, circle things, highlight things, whatever you need to do, and then start taking the exam, having gotten that knowledge sort of down on the periodic table, if that makes sense. So, talked about all atoms of the same type have the same number of protons. Number of protons never changes. What can change, though, are the number of neutrons. So all atoms of the same element do not have the same mass. Some of them will have a little more or a little less because of the varying number of neutrons. These are called isotopes. So same number of protons, different number of neutrons. And then all elements have their own unique percent natural abundance of isotopes. So the percentage of chlorine atoms that are going to be, let's see, what is chlorine? Chlorine's like, I think 35 and 37 are the abundant isotopes. Or, 35 and 37. So if we were to look at any sample of, for example here, neon gas, there are 3 different isotopes of neon. One of them is neon 21, there's also neon 22, and then the most abundant one, which is neon 20. And they exist in these percentages. So only 0.27% of neon is neon 21. Less than 1%, right? Almost 1/4%. About 10%, 9.25% is neon 22, and then 90% of all neon on Earth is going to be neon 20. And the percent abundances have to do with how neon is either generated or where it came from. Different, usually radioactive decay of heavier things. So we've got a couple ways that we can write out isotope symbols. Because now instead of just saying, okay, it's this element, well, the element symbol tells us how many protons it has. But we need to also add in there now something about how many neutrons there are. So the way we do this is we include the mass number and the atomic number along with the symbol. Oops. So, for example, our neon 20 has a mass of 20, and it has 10 protons. So if we wanted to figure out how many neutrons there are in neon 20, it's going to be the mass number minus the number of protons. So 20 minus 10 means that we have 10 neutrons. And then for neon 21, now our mass number's gone up by 1. The number of protons is the same. That just means we have 1 more neutron than neon 20. So it would be 11 neutrons here. And then for neon 22, it would be 22 neutrons. So that top left number is the mass number. The bottom left number is the number of protons, or the atomic number. Don't ask me why mass number is A and atomic number is Z. Yeah?
I have a question about, are those ratios of what percentages of neon are neon 22 or neon 20? Are those percentages consistent with any sample of neon?
Yes. There are some things that won't have consistent percentages depending on where you get the sample, but this one? Yeah, there are some things that won't be consistent. Well, it's not till the very, very end, but we'll talk about like carbon dating. So in the atmosphere, well, the most abundant form of carbon is carbon 12, but there's also carbon 13 and I think carbon 14. And carbon 14 is created in the upper atmosphere because of ions from the sun bombarding the atmosphere. So you create this carbon 14, and that's always kind of being generated at the same rate all the time. And then when plants and living things are alive, they're constantly taking in some of that carbon 14. And then the carbon 14 has a half-life of 2,000 or 5,000 years? 2,000 years. I don't remember exactly what the half-life is, but it's a relatively short half-life. And so the way they do carbon dating is they will take a sample of something that's died because it stopped taking in carbon 14, and they can look at the ratio of carbon 14 to carbon 12 inside of that sample. And that rate of, or the percentage of carbon 14 will go down for however old the thing is, because it stops taking in carbon 14 when it died. Sorry. Yes, thank you.
And then wouldn't the letter be an E or why?
Oh, that's N for neutrons.
Oh, okay.
Yeah. Is that your question? Yeah, okay. Thank you. Yes. That should be 12. I mean, you passed my test. Come by later for a sticker. I don't know. Okay, so the mass number is A. That is always going to be the number of protons plus the number of neutrons. So again, our number of neutrons will be the mass number minus the atomic number. Again, don't know why those letters are switched. So a mass number minus atomic number will give you the number of neutrons. And again, a question that I might ask on an exam would be, actually probably on the next, in a couple slides, would be something like, how many neutrons does bromine 81 have? And you got to look at the periodic table, see bromine has 35 protons. Maybe I did hit my head last night. 35 protons, so you could say, so here, let me write this out. So we have bromine, 81, and it has 35 protons. So I might say, how many neutrons does this isotope of bromine have? And then you would say, oh, well, it's just 81 minus 35. That is 46.
Where do you get the mass number?
The mass number is this one.
Yeah.
So that would be given.
Okay. Like,
So
we're not gonna
that's,
have to find what the mass number would be?
well, an example of a question that might be asked like that is an isotope of, let's just use bromine again. An isotope of bromine has 45 protons, or 45 neutrons. 45 neutrons. What is its mass number? So you'd find, if I wrote it like this, just gave you this information, then you'd have to look at the periodic table to get the atomic number. 35 plus 45. Add them together.
So that would be,
Because that'll give you the mass number, the number of protons plus the number of neutrons.
but 35 plus 45 is only 80.
Yes. The mass number can change based on the number of protons, or based on the number of neutrons.
Oh, so, okay. There we go.
Cool. Good.
So, just,
Yeah.
so it would, so the mass number is the number of neutrons, which would be given, plus the atomic number.
Yeah.
Would be, okay.
Yep. Yeah.
Is there a most common amount of neutrons that is it most common for atoms to have the same amount of neutrons and protons, or?
Yes. Roughly. Yeah. They're most stable when they have the same number of protons and neutrons. And then that only goes up to a certain mass. So it's getting a little bit sidetracked, but we're doing good on time. If you think about, we talked about, it's related to. We talked about how like charges repel each other. So protons both or all have positive charges. So how are all of the protons stuck together in the nucleus? They can because of something called the strong force, and which is, the strong force is they have to be like touching each other for the strong force to work. It's kind of like magnets, right? Like a magnet can be really strong when it's on the thing that it's stuck to, but as soon as you get it even a little bit away, it's way weaker. That's kind of like the strong force. And so if you can get these protons stuck together close enough, then the strong force can take effect and stick them together. But if you get too many protons grouped together, then they're still able to overcome the strong force. And then that's where neutrons come in, because neutrons don't have a charge. They're not adding any force that's going to break apart the nucleus, but they add more strong force to hold those positive charges together. So for most of the periodic table, there's roughly the same number of protons and neutrons. But when you start to get up to the heavier and heavier elements, there's a lot more neutrons than there are protons. Good question, by the way. So we talked about this first notation method where we put the mass number to the top left, the atomic number to the bottom left, and then the chemical symbol. We can also write out isotopes as the symbol or the name with a dash and then the mass number. Because we can always go to the periodic table, and look up the atomic number. So it's not really necessary information that needs to be given. And a lot of stuff in chemistry is about how do we present the minimum amount of information necessary, which is why we don't write out ones most of the time, because they're unnecessary. I wouldn't put a negative or positive charge if there wasn't at least a 1 there. Or I wouldn't write one element down if there wasn't at least 1 there, and if there were more, I'd tell you that with a 2. So for this, we don't need to write down the atomic number because we can find that from the periodic table. So in this notation, it's neon dash 20, so that means the mass number is 20. We can figure out neon has 10 protons, so there must be 10 neutrons. So I could ask the same questions that I asked like here, right? How many neutrons does this have? But written out like this. Right? Say neon 22, how many neutrons? And it would be the same mass number minus the atomic number gives you the number of neutrons. All right, so what are the atomic number, mass number, and symbols for the chlorine isotope with 18 neutrons? Chlorine has 17 what? Protons. So is the do I put the 17? Yeah, bottom left. So 17 plus 18 is 35. And then the other way to write or one of the other ways. Yeah, so it could be chlorine dash 35 or chlorine dash 35. I see this happen a lot. I don't think that these are very hard, and I hope that you see them that way. There are things to memorize, so when you're studying, don't just completely skip over these things and think I'll know them for the exam. Make sure you get some practice in, because they can be easy points, or they can be easy points to lose. All right, so how many protons and neutrons are in the potassium isotope given here? So first, how many protons? Yep, the trick is just remembering which number is which. So how many neutrons are there? $39. Minus 19. I think I heard somebody say it. 20 neutrons. Well, that's pretty much all there is to that. Just remembering what each number means and represents, and then remembering that the mass number is made up of the protons plus the neutrons. And you're probably hoping we could get away in a whole chapter without having any tricky math. It's not that tricky, but it is kind of a lot to remember, and there's a lot of opportunity for mistakes. But how do we calculate? So these numbers on the periodic table, like for potassium, it's 39.0983. And so far, all the numbers that we've talked about are like whole, nice, round numbers. So the way that we get those is through this atomic mass calculation. And it's representing the mass of that element based on the natural abundance, so the percentage that exists in real life. The natural abundance times the mass of that isotope. So for chlorine, there's chlorine 35 and there's chlorine 37. So 75% of it is chlorine 35, and then the other roughly 25% is chlorine 37. Now, the atomic mass units are a little bit off from the mass numbers that we've been talking about because the masses aren't exactly 1 for a proton or a neutron, and then there's also electrons. So I'll always give you the mass number with a certain number of decimal places. So this is actually 34.97 and 36.97. So to calculate the atomic mass, you have to divide the percentage by 100 to get it as a proportion. That's a key part. Very often gets missed. Otherwise, you'll get ridiculously huge numbers. So you take your percentage, you divide it by 100, then you multiply it by the mass that is that abundance. Right? So 75.77% is 35. So we took 0.7577 times the mass of 34.97. And then you add that to the proportion, 0.2423, times the mass of chlorine-37, which is 36.97. And then that can go on for however many isotopes there are. So here's the generic formula. I think, well, in my opinion, this is the best way to write it out. I think it keeps it more organized. So it's the fraction or the proportion of isotope 1 times the mass of that isotope. And then if you write it out like this, then you can put the numbers over here and then just add them up going down to get your final answer. So leave that over here. I remember this being the trickiest math. If you have any experience with statistics, this is a weighted average. If you don't have any statistics, then that won't help. I didn't learn what a weighted average was until grad school, so. They're not very tricky, but they're like not very common either. All right, so if we have magnesium with 3 naturally occurring isotopes with those given masses, and then we're also given the abundances of each of those, calculate the atomic mass of magnesium. One of the tricks here too is that the order of the masses lines up with the order of the abundances. Right, so this first, I can use a highlighter for this. The mass of 23.99, that is 78.99%. Pick a more different color. It's maybe too dark. So 10% lines up with 24.99, and then the 25.98 is 11.10. So we need to take each of those abundances, divide them by 100. And to do that, you just move the decimal place over to the left 2 places. So 78.99 is going to be 0.7899. And that's going to be multiplied by 23.99. And 0.1000, that's the 10%, times 24.99, and 0.1110, so it's 11.10%, times 25.98. So we're going to do each of these and then add them together. So 0.7899 times 23.99. So that first one is going to be 18.9497. 0.1. Oh, I guess I didn't need to do that on the calculator. That's going to be 2.499. And 0.111 times 25.98. 2.88378. Yeah. So you could really take your percentage and just put the decimal at the beginning of the percentage.
So you skip the divided by 100 when you do that?
It's the same thing. Dividing by 100 will give you that result. So do want to point out here, so this is, again, a weighted average. So you'll see that even though the masses of these are all roughly the same, the result of each of those little pieces gets smaller based on the percent of the total that it makes up, right? So very little, or well, roughly 10%, I guess, but fairly little of the 24.99 or 25.98 is represented here. And so when we do those multiplications, it's 2.499 and 2.88, right? So they get smaller. So that's the weight of those. Whereas most of it is going to be from this 23.99. And then adding those numbers together, plus 18.9497 will give us 24.33. We should have, I guess, just two decimal places here. So 24.33 AMU is the atomic mass.
So for the first part, to get those numbers, how did you do it in a calculator?
Oh, to get from here to here? That was just 0.7899 times, whoops, 23.99.
Okay. So we just do that for all three and then add those three up?
Mm-hmm. You can type this whole thing into your calculator all at once. You actually don't even need parentheses, because it'll do all of the multiplication first and then add. Oh, because we need to use the proportion and not the percent.
So we're just going to be moving the decimal every time we do that, or?
If you're given percentages. So it's the same as if I take 78.99 and divide it by 100. I mean, I guess I don't really need to type it into my calculator because it's going to be, and you could try this, try this on your calculator too to prove it to yourself. 0.7899. Yeah. Because percentages are funny things. They're not numbers that you can really use for anything. They're just, the reason that we multiply them by 100 is to make them sort of whole numbers instead of fractions of a number. Yeah. So your percentages should always add up to 100%. Proportions will always add up to 1. And when you do an atomic mass calculation, you're always going to get a number, if you're doing it correctly, that is similar to the atomic masses of the isotopes. Right? If you get a really big number here or a really small number here, then you've done something wrong. And it's going to be different than just taking the average of the three numbers. Which actually, so if I do the average, that's 23.99 plus 24.99 plus 25.98 and divide by 3. Then that result is 24.99. Right? So you get a different result because we changed how much or how important each of the numbers going into the calculation is. This is definitely one to practice. Any more questions? This is the last slide of the chapter. So.
So how do we know which one to divide by 100? Because I see like, okay, the 23.99 goes to like the 78.99, but you only divided the 78 by like a percentage.
You always divide, yeah, it's just the percentage that gets divided by 100.
Oh,
Yeah.
What does the U stand for in?
Atomic mass units. Yeah, so we use atomic mass units because it's like times 10 to the negative 27 kilograms is how much a proton weighs. I guess we'll end 5 minutes early then.